All right, so this is going to be the derivation of the single slit formula, which is a good explanation of what in the world did Mr. Chorman talk about in that last video. Just throwing all these ideas at us, all right? Again, very abstract. Take the time. The textbook has 5 pages, all right, of text with a big font, which means that it's not much reading, okay? They get to the point, they explain it quite well. So read through the text, okay? Again, we're talking about diffraction and interference, okay? Bending of a wave, and then all these little wave fronts. Think about it in terms of Hoyan's principle, okay? They're all interfering with each other, and we end up with an interference pattern that we're detecting with light, okay? That's what is happening here. So what we have, what we consider is our incident plane wavefront, all right? Our light coming towards the screen. Okay, and what's going to happen is that this light hits this opening. Okay, and what we're going to do is we're going to separate where the light's hitting into different positions, different points. All right. Again, treating this like Hoyan's principle. Each of these is its own source. Okay. We're going to split it up into fourths. This opening into fourths. Okay. So therefore, we end up with 5 points along this opening, one at each edge, in the middle, and then in the middle of both of those. Okay. So we have our 5 points here. What we're going to say is that each of these points is the emitting array, all right, that travels out towards the screen on which we are going to shine the light of the interference pattern, all right, and that screen is sufficiently far away that each of these point sources is traveling parallel to the other. Okay, that is a very, very big approximation. That is not physically accurate. Okay, but we are going to assume that to make the math easier for us here. Okay, so again, if you want to write this out somewhere, just big, bold, something. This is an approximation. This is not the actual derivation. Okay, but just know that it's good enough for this. Okay, and it's really close to the actual thing. All right. So what we end up with here, okay, are some parallel lines. What we're going to assume is that we have a line connecting point 3 to the midpoint of the central fringe, and then we have some distance here, all right, that's going to be the distance to the first dark fringe, okay? Now, the angle from that line connecting the midpoint of the central bright fringe and 3 to that first dark fringe, we're going to call that theta. That's a very, very important angle. Okay, that's the angular separation that I've been talking about in the previous slide. All right, so what we're going to say, because these lines are parallel, we go over to this next image here. All right, is that the angle between the horizontal and the ray coming from 1 and the horizontal and the ray coming from 3 are both theta. Okay, we can say that they're approximately such. All right, so what we end up doing here, okay, we're going to draw a couple of small right triangles. So this is in section 3 here, okay, what I've done, all right, you can put this on your page, pause it right now, okay, draw what I have so you have it too, all right, and then replay it, and I'm going to explain what in Sam Hill is going on here, all right. So what I've done, okay, is that I've drawn a right triangle, all right, in here, connecting point 1 and using point 1, the line segment between 1 and 3, all right, and the 2 rays that are going to P. Now, again, this is an approximation, so these 2 thetas we're saying are equal, even though we know that they're not. All right, we're just saying that they are. But if we've drawn a right triangle here, okay, what we need to consider is that this angle here is 90. Okay, if that's 90, then this angle here must be 90 minus theta. Then we have 90 right here, so this angle right here must be theta, okay? So, again, pause me, rewind me, review this, okay? We've got to make sure we get the geometry straight. So, what we have here between points 1 and 3 is half the width of the opening. The width of the opening we've defined as b, so if you want to write that somewhere, b is equal to the width of the opening. All right? Given that b is the width of the opening, okay, b over 2 is the hypotenuse of this triangle, all right? So if point P, really quickly, think about this, if point P is the position of the first dark fringe, all right, then the path difference, all right, from P to 1 and P to 3 must be half lambda. All right, good, okay? So what we end up with here, all right, is this triangle. The path difference is this side of the triangle right here, so it's lambda over 2. All right, we've got a right triangle here. This is b over 2, and this is theta. Again, pause me, rewind me, go back through exactly how I created this triangle. All right? So what we see here through our trigonometry is that b divided by 2 times sine of theta, all right, is going to be equal to lambda over 2. What we see, b times sine theta is equal to lambda once those 2's cancel out. All right? So this is our main formula here that we're going to be using. It turns out, right, that this is a really small angle. Theta is a really small angle because we're going to say that the distance from the screen to the barrier is quite large. Okay? If that's the case, all right, we have our small angle approximation. And hopefully you guys remember this from trigonometry. With our small angle approximation, all right, think about our unit circle. All right, what do you think about our unit circle? So what is this hypotenuse going to be equal to? It's the unit circle? 1. Okay. This right here, this is sine theta. And this right here, this is cosine theta. Okay. Now if we assume theta is in radians, all right, what is theta? Well, I don't know if you guys remember this with the unit circle, but it is the arc length, all right, of the circle, all right, with radius 1. So this arc length right here, this is equal to theta. Now if you have a really small triangle, okay, let's consider, a really small angle theta, right? Look at this. That little arc length right there is really close to this side of the triangle. So what we end up seeing is that sine of theta, when theta is in radians, is approximately equal to theta. And then what else do we see? We see cosine theta is approximately equal to 1. All right? It gets closer and closer there. Check out, plug in some values of some really small angles in radians, and you'll see sine of theta pretty much is equal to theta. So this is a big thing. Because theta is so small in this problem, what we end up with is we invoke the small angle approximation. We call it SAA. Okay, not side angle, sorry. Small angle approximation. All right, we'll write it like that. And so what this tells us is that theta is going to be equal to lambda over b with some rearrangement of the previous equation. Okay, so this is really important. What this tells us, okay, what we call this is our diffraction single slit formula. All right, this is what we're going to be using to determine that angular position, okay, based on what the wavelength of the wave is and the size of the opening of where that first dark fringe is going to be. Okay, so this tells us the angular separation or position of the first dark fringe. Okay, so there we go. All right, that is your derivation. We have a quick little example problem to show you here. All right, so for this example problem, we have a diffraction pattern that forms when the wavelength of light 675 nanometers, gotta make sure we know our prefixes, passes through a single slit. Determine the angle that locates the first dark fringe if the width of the slit is 18 micrometers. So here we have diffraction. Remember how I said for noticeable diffraction, you need to have lambda and b be approximately equal? Well, in this case, they're off by 2 orders of magnitude, but that's okay because it's light, okay, and we're not talking. And in this case, we still get diffraction and interference. Before I was talking about noticeable diffraction, like if we're using a ripple tank or any other situation. I actually have some great images of diffraction. I'm going to show you pictures that I've taken. One picture that I've taken of a creek and diffraction of waves around rocks and such. So, and you can find those easily online if you just Google the images. All right. All right. So again, this is all in radians. Just a reminder. Okay. We plug in our values of 675 times 10 to the negative 9 meters with nanometers divided by 1.8 times, 18 times 10 to the negative 6 meters, 10 negative 6 is micrometers. And what we end up with is 0.038 radians, right, using sig figs there. And if you want, you can figure out that this is about 2.1 degrees, okay? So you just get an idea of how big that angle is. And it's a pretty small angle, okay? All right, so that's it for the derivation of the single slit formula for diffraction.